Let's talk about the bond angle in relation to hybridization. The first thing I want to point out to you is that p orbitals in general are orthogonally arranged in respect to one another. So they have a limit as to what the bond angle can be, and that's 90 degrees. And this, for the most part, represents the lower limit of your bond angles when you look at molecules. And by bond angles, just to be sure that you understand, we're talking about the angle that forms from looking at three atoms. So let's say this hydrogen, carbon, carbon bond angle, we'll be talking about the bond angle right here. Okay, now since the lower limit is 90 degrees for p orbitals, what you're really seeing is that as you lower the bond angle, looking from molecule to molecule, you're actually increasing the amount of p content, and conversely you're also decreasing the amount of S content. So I want to show you an example here with these cycloalkane molecules, the triangular, square, pentagonal, and hexagonal structures. If you look at the bond angles in between those carbon-carbon-carbon bonds, you have 60 degrees for the triangular structure, 90 degrees for the square structure, 108 for the pentagonal, and 109.5 for the hexagonal. And the interesting thing is that the hexagonal structure, technically speaking, should be 120 degrees. But this molecule is actually not planar as depicted by this drawing. It actually breaks off from planarity, and in doing so decreases its bond angle to 109.5, which is the preferred and ideal bond angle for tetrahedral structures like the carbon that we have right here. So this molecule will represent our true sp3 hybridization, since it has the perfect bond angle for tetrahedral structures. But the other ones where you decrease the bond angle are going to have greater p content. And so you could expect that, okay, this will have the typical sp3, but this will have more than 3 p orbitals in content, and this will have even more, and that will have even more p content. And you may ask, well, what is going on? How can you have more than 3 p orbitals? Well, the thing is this, collectively, you can only have 4 orbitals. So if you were to increase the amount of the p orbital to, let's say, 3.5, the amount of the s orbital within the hybridization has to go down by 0.5, so that together they give you 4 orbitals. So this is 3.5, this is 0.5, and in doing so you can kind of adjust the amount of p content and s content. But then you may ask, well, but you only have 3 p orbitals per atom within the second energy level, so where are you getting the extra p orbital from? And it actually comes from the neighboring bonds that don't make up that bond angle you're looking at. So here we're looking at the carbon-carbon-carbon bond angle, but next to it you have the carbon-hydrogen bonds, which are also hybridized with an sp3 hybrid orbital. So you end up basically borrowing some of the p content from the neighboring CH bond, and at the same time, since you are increasing the p orbital at the expense of the s orbital, the amount of the s orbital that's being decreased is given to the CH bond. So what you see is the opposite trend for that CH bond. You have more s content on the CH bond as you go from the hexagonal structure down to the triangular structure. And the experimental outcomes of this are rather amazing to see, because the hybridization will tell us exactly what's going on. Now keep in mind, however, that the triangular structure is kind of violating a little bit the lower limit that we're meant to have of 90 degrees. So you're going to see some discrepancies involved with this structure. But focusing on the carbon-carbon bond, we see that the amount of S content is less in the triangular structure than the square, which itself is less than the pentagonal, which itself is less than the hexagonal structure. So you have less S content, and if your S content goes down, the bond length increases. So looking at the trend here, right, the S content from left to right is actually gonna go up, right? So from left to right, the S content in the carbon-carbon bond is increasing. And so you should expect to see that the carbon-carbon bond lengths will decrease going from left to right. And if you start with a square structure, you see that that's exactly what's happening. You start with 1.555 angstroms and you go down to 1.536. That's a direct result of the fact that the carbon-carbon bond increases in amount of S content. Now, The triangular structure kind of breaks that trend. In fact, it is the shortest out of all of them, not because of the fact that the hybridization is not predicting this correctly, but rather because we have broken the lower limit of 90 degrees. We're down to 60, and the actual bond here is not your typical cylindrical sigma bond, but rather you have bent orbitals that are kind of like meeting at an angle. And so it's not exactly the same picture. You're kind of comparing apples to oranges, and that's why I'm saying sometimes the trends get broken down by this triangular cycloalkane. All right, but check this out. Let's now look at the carbon-hydrogen bond. Going from left to right, what I did say is that the amount of S is decreasing, right? You have the most S content on the triangular structure within the CH bond, right? And so we would expect that that CH bond would be the shortest one. And the CH bond here on the hexagonal structure, which has the least amount of S content, in comparison to each other, um, should be the one that is the longest. And that's exactly what we see. We start with a bond length of 1.083 for the carbon H bond, CH bond, and we increase it all the way to 1.119 angstroms, and that's just phenomenal. You see that exact trend based on the idea that the S content is decreasing going from left to right for the CH bond. All right, as depicted by the diagrams here. All right, now the last thing, the bond dissociation enthalpy. If you look at the bond dissociation enthalpy of the carbon-hydrogen bonds, a similar idea presents itself. Once again, the S content is decreasing as we go from left to right. We decrease the S content, and the S content means that you see less of the nuclear charge. So you're going to be easier to be removed from that atom since you see less positive charge. So S content going down from left to right means that the bond dissociation enthalpy should actually go down. And that's what we see generally speaking. This starts at 444 kilojoules per mole, drops down to 409, which then drops down to 400. And we kind of break the rule a little bit here because technically speaking, this structure is not a planar structure, at least not as much as the other three original cycloalkanes. But generally speaking, we see the trend, following through. And it's phenomenal to see that with this simple picture of looking at whether something has more S content or P content within your hybrid orbital, you can make these trends. This is a technique we're going to exploit at least once more in this class, so it'll be good for you to get familiar with it. Okay? Um, just as a little summary, you can use hybridization to predict series of bond lengths in terms of increasing bond length or decreasing bond length. Same thing for both bond angles. They can tell you a little bit about the hybridization of the carbons involved. And you could even have some arguments for the bond dissociation enthalpies of those CH bonds based on hybridization. So hybridization is a very powerful technique, but it has limitations. Beyond organic chemistry, hybridization actually is quite terrible. It doesn't really predict things much. And even though you might have seen it in general chemistry applied to transition metals, the truth of the matter is that no inorganic chemist that works with transition metals ever invokes hybridization to explain anything with transition metals because the theory is just not robust enough to make any accurate predictions with them. Molecular orbital theory tends to be the better way about it, and we will be discussing that in the next video. So see you then.